Okay, were there any questions? No. Let me review just a little bit about the equivalence points here. So in the buffer region, the calculations are very fast. So we had the 1/11th, which we aren't going to observe because it's too low, and the 1/4 also we aren't going to observe because it was too low. But the 10/11ths and the 3/4 we should observe those. So those were fairly straightforward to calculate. Just to review, the 3/4 equivalence point means I've neutralized 3/4 of the acid. If I've neutralized 3/4 of the acid, then I'll have 3/4 of base, the conjugate base, which is the product, and 1/4 of the acid remaining here. And so this comes out to pKa plus the log of 3/1. And the log of 3 is plus 0.477. So this is pKa plus 0.477. If we flip this around, then that's the 1/4 equivalence point. And it would give us the log of 1/3. Just be inverted here. And that would be 1.267 minus 0.477, which would bring it below the initial pH, which was 1.10. So these two I have asterisk here. But this one we should see. So 1.267 plus 0.477 gives us 1.744, looks like. And then the 10/11ths we got earlier, that was just the pKa plus 1, the 2.267, which rounds to 2.27. And so this gives us the buffer region, but we can see it stays fairly flat near the pKa. But as we get close to the equivalence point here, then we'll see the rise. So at the equivalence point, we would have added 50 milliliters. Here we can't use the Henderson-Hasselbalch because we're outside this buffer 1 region here. And so at the first equivalence point, we had to do the solution dilution. 25 milliliters of oxalic acid plus 50 milliliters sodium hydroxide gave us 75 milliliters. The equivalence point, the moles are the same. So we have equal amounts of oxalic acid and sodium hydroxide. That's what we have here. And so it neutralizes each other. So the oxalic acid and sodium hydroxide neutralize to form salt. However, you have to take a look at the salt. You know, we have 3 different types of salts. We have the neutral salts, like sodium chloride. We have the acidic salts, like ammonium chloride. And we have actually 3 types of salts. We have the basic salts, like sodium carbonate, and we have the amphoteric salts. So that's actually 4 types of salts. And so 4 types. Actually, it's a little bit more complicated because some of these can be more than one. So we have neutral, sodium chloride. We have acidic, be like ammonium chloride. We're going to have basic, which would be like sodium carbonate. We have amphoteric, which would be like sodium bicarbonate, or in this case, sodium hydrogen oxalate. I used OX for the abbreviation for oxalate, and then we have mixed. Mixed would be like an acidic cation, like this, paired with a basic anion. So ammonium nitrite would be an example. Ammonium would be acidic, nitrite would be basic. Nitrate would be neutral, but nitrite is basic. And so this will be mixed here. Well, anyway, this is going to be an amphoteric salt. When we have an amphoteric salt and we have the concentration here, our step 2, when we go to step 2 here, what should we do? An amphoteric salt can either donate, i.e. Ka, or it could accept, i.e. Kb. And so it depends on the collision. In some collisions it'll donate, in other collisions it'll accept. And so it just depends on that, and it's somewhat random. Usually there's a preference. So for example here we see that the Ka is 10 to the minus 5, whereas the Kb is 10 to the minus 13. What this means is that the hydrogen oxalate or bioxalate is a much better acid than a base. And so that gives us different ways we can approach this particular problem. One approach is to ignore Kb entirely and just call it an acid, because this is 10 to the minus 13, which is close to 10 to the minus 14, like water. And that would get us close, but it's also ignoring these collisions entirely. These collisions will happen just at a much lower frequency. That's one approach. Another approach that we could try is stepwise, but normally when we do stepwise, we look at all hydronium ion producers. But what do we have? Here we have a hydronium and a hydroxide. So how should we handle that? Should the hydroxide that's generated neutralize all the hydronium, or as much as possible? But that's going to perturb the equilibria, and we're going to get into this endless loop. And so the best approach for this is when we have an acid and a base in solution, then we should do this simultaneous. We didn't have to always do it simultaneous. So for example, if the acid and the base were related to each other, i.e. conjugates, if the acid and the base were conjugates of each other, then we don't have to do it simultaneous. Because if the acid and base are conjugates of each other, then these two equilibria describe the same thing. And so if we go back here and look in the buffer region 1, in buffer region 1 we have the acid, which is oxalic acid, and the base, which is sodium hydrogen oxalate. And when we look at the that is the Ka for this, and let's say the Kb for this, although this is also going to have a Ka. When we look at the Ka for this and the Kb for this, it describes the same equilibrium. And so when they're conjugates of each other, then we don't have two equations, because when they're conjugates, then they're equal. The Ka for the acid is equal to the Kb for the conjugate base, because they describe the same equilibria. But in this case, they don't, because when I look at the equilibrium, this is the equilibrium between bioxalate and oxalate. This is the equilibrium between bioxalate and oxalic acid. These are two different equilibria. Versus when we look at a typical buffer, in a typical buffer we have HA plus water goes to hydronium and A minus. And then we look at A minus plus water, and goes to HA plus hydroxide. And so when we look at these two equilibria, they're the same. HA and A minus and HA. However, when we look at these two equilibria, they're different. And so this one we could use the Henderson-Hasselbalch, HH, because these are equivalent. Equivalent equilibria just described in terms of pH versus pOH. These aren't. And so in order to connect the hydronium, these are going to be connected here. But in order to connect these, we need Kw. The hydronium here and the hydroxide here. So when we're at the equivalence point, we have the salt, and it depends on the type of salt we have, so we have to consider what type. In the previous titration, we had a neutral salt, sodium chloride, so the pH was 7. In this case, we're going to have an amphoteric salt. Now, what is the pH of the amphoteric salt? Well, we have to do that simultaneous. If we do that simultaneous, we come up with this one. This is the pH equation for the amphoteric salt, which you don't have to derive. This will just be given. And this is for amphoteric salt, or amphoteric species. So we just get the pKa for the amphoteric. The pKa for the amphoteric we had calculated earlier. That's the pKa2 here. And the pKa2 here is 4.275. So in other words, if I want to determine the pH here, the pH is going to equal the pKa for the amphoteric species, which is HC2O4 minus, plus the pKa for its conjugate acid. Conjugate acid of this is going to be H2C2O4 divided by 2. So I have those numbers that we had calculated earlier to get this. So 4.275, the first one, 4.275 plus the pKa for oxalic acid, which was 1.267. Divided by 2. So what does that come out to? .771. And so if we go back to our titration curve, then we're going from here 2.27 up to 2.77. So between 45 and a half and 50, we're going to go up from 227 to 277 here at the equivalence point. Now, once we go past, then we have excess base. But this is a diprotic acid, and so it's going to behave differently, the excess base. And so that's going to throw us into buffer 2 range. And so let's go ahead and we have two different choices. If we're in the buffer 2 range, we can do the calculation. As a shortcut method or as a long-handed method. We'll do both for one of them. Just need to make some more pages. So once we're past the equivalence point, now we're in buffer 2 range. And so from this equivalence point here to this equivalence point here, this is where we're going to be focusing in this range here. So what I could do is we could do a calculation for, let's say, 1/4 the second equivalence point, or 10/11 the second equivalence point, or something like that. Or half the second equivalence point, or whatever else we want here. And so at the half of the second, 1/2 of the second equivalence point, the pH is equal to pKa. But it's going to be the pKa of bioxylate, not of oxalic acid. And so let's maybe do this one as a long calculation. So the short method is we just know halfway in between we've neutralized half of the second proton. All right, so this is going to take us to 50. This will take us to 100. So this should be at 75 milliliters at the half equivalence point. And so we'll do the long calculation here. You know, plus 75 milliliters of sodium hydroxide. 75.0. So we'll take our original 25 milliliters of the oxalic acid plus that, and so this is going to give us a total of 100 milliliters. And then what we're going to do is we're going to do the solution dilution, our step I here first, and we're starting all the way at the beginning, at 0. I don't start from the first equivalence point on. And so the oxalic acid was a 25 to 100 dilution, 0.100 molar. So this should be 0.0250. All right, and then the sodium hydroxide is going to be a 75 to 100. 100. This is going to give me 0.0750. So this is the initial step, and just to get the initial reaction mixture, and then we'll do the reaction as step 1. The reaction is going to be the strongest acid, oxalic. I'll just write it out this time, plus the strongest base, sodium hydroxide. We do this one at a time, even if we have excess sodium hydroxide. And that's going to form sodium hydrogen oxalate plus water. And so here, the initial oxalic acid is 0.0250, and the sodium hydroxide will be 0.0750, and this will be 0, water. All right, the limiting reagents is going to be oxalic acid, so that's going to go to 0. And we're going to lose a quarter of this, so this is going to go to 0.0500, and this will go to 0.0250. The change is complete because K is very, very large. So I'm skipping writing some of the stuff there. All right, is this a buffer? This is not a buffer. And so in step 2, what we're going to do is we're just going to take the strongest acid remaining. The strongest acid is going to be sodium hydrogen oxalate plus the strongest base. Well, we have leftover strong base, sodium hydroxide. That's going to react until there's nothing left to react it with. And this is going to form Na2C2O4, sodium oxalate plus water. So we'll drop down the sodium hydrogen oxalate that we just produced here. That's going to go down here, 0.0250. And then we have this sodium hydroxide, which we'll have to drop down here. It's going to be 0.0500. Did I make a mistake? Let's see. 75 milliliters. Oh, I did make a mistake. Shoot. Do you know what my mistake is?
What was our molarity of?
Yeah, the oxalic acid was 0.200 molar. So not 0.100 molar. The reason I realized I made a mistake is because the limiting reagent is going to be this, so I'm just going to have excess strong acid, weak acid at the end of this, so this can't be it. The oxalic acid, I made a mistake here. The oxalic acid should have been 0.200 molar. And this is going to give us 0.0500 molar. This is going to give us here 0.0500 molar. Okay. And this would be 0.0250. And this should be 0.0500. Which is going to mean this is going to be 0.0500. And this will be 0.0250. All right, now it makes sense because I've neutralized half my acid with the sodium hydroxide. So this is the second equivalence point here, and I've neutralized half the acid. And so at equilibrium here, I'm going to have 0.0250 molar acid left, and then 0 molar. This used to be base, now it's acid because it's the strongest acid that's left. And I'll have 0.0250 molar. Okay, so now I have an acid and its conjugate base. So this is a HH buffer here for step 3. So step 3, I'll just use the Henderson-Ausbach. That is, the pH is equal to pKa for the acid. The acid here is just going to be hydrogen oxalate plus the log of the base. The base here is going to be oxalate to acid. The acid is going to be hydrogen oxalate. And if you look at the concentrations, they're the same. So this is log of 1. And so the pH is just equal to the pKa. Or hydrogen oxalate. So we could do the same thing here that we did for the others. So for the others, we got the points rapidly. Let's do the same thing here. So we know the pH here is equal to the pKa 2, for oxalic acid. All right, but the only tricky thing here is we're starting at 50 milliliters. And we're ending at 100 milliliters. So where does the 1/4 equivalence point come in? And the 3/4 equivalence point. How many milliliters? Well, to get to half equivalence point, that required how many milliliters? 75. That would be halfway between 50 and 100. So what would be 1/4 of the way between 50 and 100? 62.5. And 3/4 of the way between 50 and 100 would be 87.5. All right, so at the 1/4 equivalence point, the pH is just equal to the pKa minus 0.477, or the log of 1/3. And at the 3/4 equivalence point, the pH is equal to pKa plus 0.477. Okay. Then we have the 1/11th. And so what's 1/11th of the way between 50 and 100? Okay, 54.5. Actually, what did we calculate earlier for the 1/11th? Yeah, 4 point. Or we just take 1/11th of 50. Actually, if I want the 1/11th, I'll just do it and calculate it. So it's going to be 50 plus 1/11th of 50. It's the total distance is 50, and we're starting at 50. And so that's going to equal. Is it? All right. 54.45. All right. Thanks. All right. How about the 10? Well, at the 1/11th, the pH is equal to pKa minus 1. At the 10/11ths, we're going to be at what? .45. So it's just 50 plus 10/11ths of 50, which is 95.45 milliliters. And there we're going to get a pH that's equal to pKa plus 1. And so we can get these points quite rapidly. We can also do this. If we know the pH is here, you know, for example, the pKa2 was 4.275. So pKa2 is 4.275, and then pKa minus 1 would be 3.275, and pKa plus 1 will be 5.275, and this would be about 0.4 whatever, 3 point something and 4 point something here. You can calculate those. And so let's say I wanted a pH of 5.00. How many milliliters total sodium hydroxide would I have to add? And so an example of going the other way, here we went from equivalence point to pH, but here we're going to go from pH to the equivalence point to the milliliters of total NaOH that we're going to add. And so let's say I wanted a pH of 5.00. Well, that's in buffer 2 region. I can see it's going to be bordered in buffer 2 region. And so what I'm going to do is I'm going to work backwards. So working backwards, I'm going to start at step 3 or whatever I'm starting at here. And I'm going to get the Henderson-Hasselbalch equation, which is pH is equal to pKa2 plus the log of the ratio here. And I want this to equal 5.00. So I know what the pKa2 is. It's right here. And so I will get the that this is equal to 4.275 plus the log of the ratio, and then subtract 4.275 from both sides. And so I'll get 0.725 is equal to the log of the base to acid ratio. And then I'll get the base to acid ratio. The base in this case is oxalate. The acid is hydrogen oxalate. and that's going to equal 10 to the 0.725, which is going to give us 5.3. 5.308 over 1, basically. Now that I have the base to acid ratio, I have to think in terms of this. So I'm going to go from the base to acid ratio to get the equivalence point next. To get the equivalence point, I have to sum up the parts. So the equivalence point is 5.308 plus 1 equals 6.308 total parts. And then all I'm going to do is I'm going to set up a ratio like this. 5.308 over 1 is equal to 5.308 parts out of 6.308 parts was converted to base. And that means I have 1 part of leftover acid out of a total of 6.308 parts. And then what we do is this top part is the equivalence point here. This is equal to the equivalence point. And so if I want to calculate the total base that's required, the total base that's required is going to be 50 milliliters to get to the first equivalence point, plus 5.308 out of 6.308 out of the next 50. The next 50 milliliters would be for the second equivalence point, but I don't quite get there. I almost get there, but not quite. And so this is going to be 50 milliliters plus, all right, just leave this in my calculator, so 6.3088, I'll do 6.308 times 50. 42.07. So that's going to bring us to 92.07 milliliters, or about 92.1 milliliters. So if I want a pH of 5.00, I'm going to have to go to 92.1 milliliters. Yeah, there's a pH of 5.00. So this we can use in the buffer region. It's quite nice to use the Henderson-Hasselbalch and work backwards. But this is a key step here. How do you go from the base to acid ratio to the equivalence point? And so this is the key step here. All right. When we're at 100 milliliters, we're at the second equivalence point. And here, so at 100 milliliters, we're at the second equivalence point. And so the second equivalence point is plus 100 milliliters. Here we can't do it because the salt we're going to get, the salt we expect is not an amphoteric salt. The salt we expect is actually going to just be oxalate. As once I neutralize all the hydrogen oxalate, all I'm going to have left over is oxalate. And so the salt here is just going to be sodium oxalate and water. And so for something like this, I have to do it the long way. And so if I start this over at the second equivalence point here, I'm going to have a total of 125 milliliters. And then starting this over, I'm starting all the way from the beginning. That is with oxalic acid, not hydrogen oxalate and sodium hydroxide. It's easier to do this way, I think. And so we look at the dilution factor for oxalic acid. We started off with 25.0, and then we're going up to a total of 125.0. This is 0.200 molar. And then the sodium hydroxide dilution factor is going to be 100 diluted to 125 of 0.100 molar. So let's take a look at these calculations here. 25 divided by 125 times 0.2, 0.0400. And then 100 divided by 125 times 0.1, 0.0800. Okay, once I do that, then I'm going to go to step one. Step one is going to be the oxalic acid, so starting all the way at the beginning, plus the sodium hydroxide. This is going to make sodium hydrogen oxalate, and so we just do one hydrogen at a time plus water. K for this is very, very large, so it's going to go to completion. And so we have 0.0400, that's our limiting reagent, and then we have 0.0800, that's our excess reagent, and we'll have 0 in this. To save time, I'll just omit the molarities for right now. So we're going to lose all our limiting reagents, so that's going to go to 0, and we're going to lose half of this, so this is going to go down to 0.0400 molar unreacted sodium hydroxide, and this is going to go to 0.0400 molar sodium hydrogen oxalate that's generated. And then we go to step two. Step two is going to be the strongest acid. Now this base is not going to act as a base, it's going to be the strongest acid now present. And so it switches from a base, conjugate base, to the acid now, because there's a stronger base around, that's sodium hydroxide. And since it's amphoteric, it could go either way. So this is going to make sodium oxalate and water. And then we take a look at the limiting reagent, excess reagent, and this happens to be stoichiometric. It's just the right amounts. And so these are going to go to 0 since K is very, very large for this reaction as well. And this is going to go to 0.0400. So all we're left with here is a basic salt. This is a dibasic salt. So if we have a base solution, then we just look for KBs. We look for hydroxide producers. So the hydroxide producers will have KB1, KB2, and KW. And so let's take a look at the numbers and see if we need to worry about. We just want the pH. And so we'll see if we have to worry about how many steps we have to do. So KB1 for oxalate is equal to KW over Ka for hydrogen oxalate. So Kw is 1.0 times 10 to the minus 14, and then Ka for hydrogen oxalate is 5.3 times 10 to the minus 5. Which gives us what? .88 times 10 to the minus 10. That's pretty small. Pretty weak base. All right, let's take a look at KB2. KB2 for oxalate ion is equal to Kb of hydrogen oxalate, which is equal to 1.0 times 10 to the minus 14 divided by 5.4 times 10 to the minus 2 from the chart. And then, of course, KW is 10 to the minus 14. So in this case, if I'm only interested in pH, I'm going to just look at the biggest hydroxide producer. And so I just do only KB1. Oops. KB1 only. KB2 is 3 orders of magnitude smaller. All right, if we're just going to do KB1 only, then this is going to be step 4, and then we'll stop, or step 3. Yeah, this is going to be step 3, and we'll stop here. All right, so the oxalate that we ended up with here initially is 0.0400. And then we're going to end up with 0.0400 minus x at equilibrium, and then x and x. And so this is just going to be x squared over 0.0400 minus x. We'll try the simplifying assumption. And so this will be x squared over 0.0400. So I'll do 1.88 times 10 to the minus 10 times 0.04, and then take the square root of that. 2.74 times 10 to the minus 6. Divided, I'm going to take that and divide it by 0.04 times 100. And this comes out to a 0.0068% change. That's less than 5%, much less than 5%, so the simplifying assumption is good here. Let's just double check our calculation. And so this is going to come out to 2.74 times 10 to the minus 6 molar. This will be the same. This is going to be 0.0400 minus x, which is going to give us 0.04 minus 2.74 times 10 to the minus 6 equals, so this comes out to 0.039999726. I'll carry some extra digits here just to check the calculation. So let's go ahead and I'm going to flip that times 2.74. Okay, so actually let me try that again. 2.74 times 10 to the minus 6. Square this, divided by 0.0399972. That's probably enough. And I get a K equals 1 point. Oh, my K is way off. Let me try that again. 2.74 times 10 to the minus 6 squared divided by 0.039999726. 1.877 times 10 to the minus 10. So yeah, it looks like it's okay. Checks out. All right, so what I'm going to do, I'm going to calculate the POH. It's going to be the negative log of the hydroxide, which is going to be 2.74 times 10 to the minus 6. .56 2, and therefore the pH 14 8.4377. It looks like I'll probably be allowed 2 sig figs, so I'm going to round the pH to 2 sig figs, 8.44. And so at the second equivalence point here, the pH is 8.44. And so phenolphthalein would work well here. Phenolphthalein changes around 9. So, and this is pretty vertical, so even if phenolphthalein has a little delay, it's not going to lead to a big error here. All right, once we're past this, the strongest acid will be water. And so this will be excess sodium hydroxide and weak base. So once we're in this region here, we'll just, pretty much we could ignore the weak base. The only time we can't really ignore the weak base is like right here, because we have so little weak base, or not, actually so little. We can't ignore the weak base. The weak base is always here. We ignore the weak base out here because we have strong base, and strong base is going to overpower it. And so we can't ignore the strong base. Well, let me rephrase that one more time. Once we're in this area here, then the pH is going to be dominated by the strong base, sodium hydroxide. So I would completely ignore the weak base out here. The strong base is going to dominate. The only time the strong base won't dominate is when we have extremely small amounts of it. When we have extremely small amounts of it, then the weak base will dominate. Maybe KW. We have extremely small amounts of both, but actually we aren't going to have work here. I guess I can't get that line back. Something like that. Just in this region here, we'll have to worry about the weak base. But beyond this, we probably don't have to worry so much about the weak base. If that's the case, then it makes this a little bit easier. So let's say I want to get to pH past 844. And so I'm going to say, let's say I want to get the pH. What pH should we do? Past 844. What pH should we try to get to? 10, 11, 10? All right, let's say I want to get to pH 10.00. How many total milliliters of sodium hydroxide do I have to add? This problem becomes a more challenging problem. And so what we're going to have to do is we're going to have to reverse all the steps. But we can't take a shortcut because we're not in the buffer range. If we're in the buffer region, we can use those shortcuts that are involved with Henderson-Hasselbalch and determining the equivalence point here. But unfortunately, we're unable to do that for this particular case. Let's see. Just gonna go down. Another couple of pages. Okay, so I have to have an idea of where I am in the titration curve because that's going to dictate how I do the calculation. So if I want a pH of 10.00, then where I'm at is in the excess base region here, past the second equivalence point. And if I'm in the excess base region past the second equivalence point, then what I'm going to do is I'm going to go forward and then I'm going to go backward. So I'm going to go forward here. Going forward it's going to be plus Z milliliters of sodium hydroxide. I don't know how many that is, but I have 25.0 milliliters of the oxalic acid. And I need to add that much sodium hydroxide. And so I'm going to go forward with step I. Step I, I'm going to have this. I'm going to have a total of 25.0 plus Z milliliters here. And then I'm going to go ahead with the solution dilution. The solution dilution is I have my oxalic acid here, and it's going to be a 25.0 over 25.0 plus Z dilution of 0.200 molar. Okay, this is going to be the initial after solution dilution. So this is the initial reaction concentration, not the original concentration, but the initial reaction concentration here. And then the sodium hydroxide, we do the same thing here going forward. It's going to be a Z over 25.0 plus Z dilution of 0.100 molar. And so this will be my initial concentration of the reaction mixture for sodium hydroxide. All right, then I'm going to do step one, which is going to be ice table. So I'll take my strongest acid, oxalic acid here, plus the strongest base, sodium hydroxide here. And this is going to make sodium hydrogen oxalate plus water. All right, for the initial, I'm not going to write the equation out. I'm just going to use this here. And so the initial concentration here is just going to be the oxalic acid after solution dilution, which I called oxalic acid initial concentration. And then the sodium hydroxide, I'll just write it like that. Sodium hydroxide initial. And this will be 0 molar. Now, I have to know I'm in the excess base region. I have to know that this is my excess, this is my limiting reagent here. And it's going to tell me how much is going to react. And so I already know what the change is. I'm going to lose all my limiting reagents. So this is going to be minus H2C2O4 initial. And this is going to be minus H2C2O4 initial. And this is going to be plus H2. Here I should use the abbreviation, but I already started, so I'm not. And so here I'm going to have 0 remaining of my oxalic, And the sodium hydroxide I'm going to have is the initial sodium hydroxide minus the initial concentration of the oxalic acid here. And I'm going to be left with this amount of sodium hydrogen oxalate here after reaction. That's the amount produced. Okay, and then continuing on, I'm going to go to step 2. Step 2, now the strongest acid is going to be the sodium hydrogen oxalate plus the strongest base. I still have leftover sodium hydroxide, and this is going to make sodium oxalate plus water. And the initial amount of sodium hydrogen oxalate I carry down from here. And so that is going to equal the oxalic acid concentration that I had initially. And then the sodium hydroxide is going to be this here. It's going to be the sodium hydroxide initial minus the oxalic acid initial. And I have 0 sodium oxalate here. Okay, now again we have to know what our limiting reagent in excess. We're in the excess base region, strong base region, so this is going to be the excess over here. This is going to be the limiting. And the limiting reagent is completely consumed. And so we're going to lose all of this. So at the end of this step 2, we should have no more sodium hydrogen oxalate or sodium bioxalate. Over here, I'm going to subtract. Actually, these two are the same. So I'm going to combine those and call this sodium hydroxide initial minus 2 times the original concentration of oxalic acid here. Not original, initial mixture. Reaction mixture concentration. And I'll end up with that there. Now, I can go on to step 3 if it's necessary. Step 3, well, the pH is going to be primarily dictated by the sodium hydroxide. So we have the sodium hydroxide here. How much additional hydroxide do you think we're going to get from oxalate? Not a significant amount. So if we could ignore oxalate, I'm not going to go on to step 3. If we have to do oxalate, then I'm going to go on to step 3. I'm going to go on, if I have to do KB2, that'll be my step 4. If I have to do KW, that would be my step 5. And so what I'm going to do is I'm going to keep going until I feel that I'm going to have the total hydroxide. And so if I think I'm going to get significant additional hydroxide, I'd continue. But what we're going to do here is we're going to assume that the total hydroxide is going to equal the hydroxide from sodium hydroxide. This is the leftover excess sodium hydroxide here, plus the hydroxide from the dibasic base oxalate, the first, plus the hydroxide from, if this is dibasic base, then it's going to make hydrogen oxalate, which is also a base, plus the hydroxide from water. So what we're going to do is we're going to assume that these ones are negligible. So this, this would be my step 3. This would be step 4. This would be step 5. but we're going to skip those. And we're going to say that that's it. If that's it, then this is what we're going to have. The POH is equal to the negative log of the total hydroxide. And so what we'll get here is the total hydroxide is going to equal 10 to the minus POH molar. And so this is going to be 10 to the minus 10.00 molar, which is going to be 1.0 times 10 to the minus 10 molar.
Isn't 10 our pH?
Oh yeah, you're right. This is wrong. Thanks for catching that. Our pH is 10.00, which means our POH is 4.00. And so the total hydroxide is equal to 10 to the minus 4.00, which is 1.0. Since I have 2 sig figs, I have 2 decimal places here. 2 sig figs times 10 to the minus 4 mole. And so we're going to assume that comes from this. And so we're going to call this the total hydroxide here. So what that means is this is equal to the initial sodium hydroxide minus 2 times the initial oxalic acid. The reaction mixture. And the initial sodium hydroxide is equal to, we don't know how much sodium hydroxide, but concentration is equal to Z over 25.0 plus Z times 0.100 molar. This is minus 2 times the initial concentration of oxalic acid. The oxalic acid is 25.0 over 25.0 plus Z dilution of 0.200 molar. So we do some substitution, and what we can do is we can get this in terms of just Z, one unknown. And then we solve for Z. When we solve this for Z, then Z is the total number of milliliters of sodium hydroxide that we have to add. All right, for this. All right. There's a way you can double check this, you know. So we solve for Z, and the way to double check this is we plug this Z back in and go forward. So we're kind of going backwards here. So once we get the Z, we do that, and then we go forward here and see if we get the same answer. And so we can go both ways, backwards and forwards. All right, in an effort to save time, I'm going to skip solving for Z here, but it's not too difficult, I think. All right, any questions with that? All right. So those are some titration, standard titration calculations. You should be able to do these kind of standard titration calculations. Let me talk more about the buffer regions here. When we're in the buffer region, the pH stays relatively flat, even though we're adding strong base. That curve sucks, but over here. The pH stays relatively flat, even though we're adding strong base. Well, that's how buffers work. We could do the opposite. We could add strong acid and go backwards You know, let's say I titrated here, but now I want to go backwards. You can go backwards by adding strong acid, and the pH stays relatively flat, as long as you're in the buffer region. Now, once you exceed the capacity of the buffer, then the pH will start to climb, because here we're going to start running out of acid component. And here we've completely run out of acid component of the buffer. Buffer has to be a mixture of acid and base, and the pH skyrockets. Likewise, if we go backwards here, we're adding acid, we're running out of base component. You know, pretty soon we run out of all the base component, the pH changes dramatically. And so that has to do with capacity. As long as we have a high capacity buffer, then we're okay. And so let's take a look at buffering actions and see how buffers work. And so, do buffers work? Let's show that buffers work by calculation. Let me take 25.0 milliliters of water. And here we're going to add 1 drop. What do you want to add? 1 drop of base or 1 drop of acid? Acid? All right, we're going to add 1 drop of HCl. We're going to make this 6 molar HCl. And so in chapter 17, we do solution dilutions. Even though the volume didn't change all that much, we're at 25.05, so we're going to go 25.00 milliliters. It changed a lot, actually, for the 1 drop of HCl. So we calculate the new concentration of HCl. And so HCl is going to be a 0.05 to 25.05 dilution of 6 molar. And so 0.05 divided by 25.05 times 6. And the concentration changed dramatically because it was such a huge dilution. So now it's only 0.01197 molar, which is going to give us a pH of 1.92. So pH 1.921.
So if you have 25 milliliters of H7 water and you got a single drop of HCl 6 molar, that's the pH?
Yeah. And so the pH went from 7.00 to 192, around 2. So that's 5 orders of magnitude. So this is 10 to the 5th weaker. Correct? Or actually not weaker, 10 to the 5th stronger, or more acidic. 10 to the 5th times more acidic, sorry. Let's just say more acidic. Water is 10 to the 5th times weaker. So would you call that a pretty significant pH change? Yeah. All right, let's make a buffer. And so the first thing is, how would you make a pH 7 buffer? What we would like is, we'd like a, if we're going to make a buffer, pH 7, we want an acid. We want an acid with a pKa of around what? Ideally, the pKa should be 7. But are there any acids that have a pKa of 7? So let's take a look and see. And so what we're looking for is a power of 7. Yes, we do. We have an acid here with a pKa of 7. The Ka is 1.0. This would give us a pKa of 7.00. This would be perfect. This would be perfect, except that it's arsenic, and arsenic is quite toxic, and so we don't want a very toxic buffer. And so let's try to find something else that's close to 7. It doesn't have to be right on 7. So for example, this would work. carbonic acid is 10 to the minus 7, but what would the problem be with carbonic acid? It decomposes. And so it'd be too difficult to work with. Citric acid, monohydrogen citrate would work here. And so this is possible. We use this as the acid, and the base would be citrate ion. So keep that in mind, that works. What else? Hydrosulfuric is perfect. This gives us a pKa of 7.00, but what's not so perfect about hydrosulfuric acid? Two things that are not so great about hydrosulfuric acid.
Doesn't it form gas?
Yeah, it is a gas, and in order to make a solution of this, you have to mix the gas with water. Is it easy to mix gases with water? No, especially when they aren't that soluble. There are more than two things wrong with this, but the two major ones. One, it's hard to adjust the concentration of H2S. Two, it's not very soluble, 0.10 molar. Three, it smells bad. And worse than that, four, it's highly toxic. This is toxic at the part per billion level, so it doesn't take much gas to kill you. So let's not use that. This is raw neg odor, by the way. Hypochlorous would work. 10 times 10 to the minus 8 is equivalent to 1 times 10 to the minus 7. So this is close. So hypochlorous is possible. We could use that. What else? Hyponitrous, this is very close. 10 times 10 to the minus 8 is 1 times 10 to the minus 7. That's very close. This is okay. This is very close. 0.1 times 10 to the minus 6 is 1 times 10 to the minus 7. So this is very close. Hydrogen malonite. Any others? This is pretty close. Dihydrogen phosphate. Dihydrogen phosphate, 6.3 times 10 to the minus 8 is very close to 10 times 10 to the minus 8. So dihydrogen phosphate looks good. Dihydrogen phosphite is good. Dihydrogen pyrophosphoric is good. Pyrophosphorate. Thiophenol. Thiophenols smell really bad. Thiols are responsible for the skunk odors. So you don't want to deal with these at all. So out of all these, which one do you think we should go with? Probably the cheapest one, because the cheapest one we can make the highest capacity. Highest capacity means more concentrated. More concentrated, the better. And so which one do you think that would be?
What's the one that was at the top right? It was like hyponitrous or something.
Yeah.
Isn't that common?
No. Hyponitrous is not that common. Citric sounds good because it's not very toxic, but the problem with citric is it's prone to being oxidized. So if you have citric, citric acid doesn't last very long because air is going to oxidize that and decompose it. So we don't want that. So let me tell you, phosphates are cheap. So I think dihydrogen phosphate is probably the best choice. So let's go with that. And so dihydrogen phosphate's close. And so this will be my acid. And the pKa of this is going to equal the negative log of, actually I forgot the number, 6.3 times 10 to the minus 8. All right, so let's go ahead and calculate that. 7.200. So we're pretty close. We're 0.2 high. And so what we're going to do is we're going to just add a little bit more acid than base. If we were at a 50-50 ratio, it would be at 7.20. So what we want is we want it to be a little bit lower at 7.00. And so that means we're going to have to adjust the ratio of acid to base. In other words, the base in this case is going to be monohydrogen phosphate. That would be our base. And the acid is going to be the dihydrogen phosphate in this system. And so we just add a little bit more acid than base and we should be right there. So this is going to be 7.20 plus the log of this ratio. And then we're going to subtract this. And so the ratio HPO4 2 minus to H2PO4 minus is going to equal 10 to the minus 0.20. Which I get as 0.63. I carried extra digits in my calculator, so that's why mine came out to 0.630. Yours may not. But I need a base to acid ratio of 0.63 to 1. So in other words, I could go like this. I could go 0.63 molar base to 1 molar acid. That would work. Versus, I could also go with 0.00063 molar base to 1 molar. I mean 0. Actually, how many zeros did I put in? 4 zeros. Yeah, it would be 3 zeros. You're right. Oh no, my pen's disappeared. Shoot. How did that happen? All right, what's the difference here between these two? This one has a higher capacity. This one has a lower capacity. But they both should have the same pH. Until I get too low. What if I did this? This is too dilute. HH equation is not going to work. Potentially fails. As you get too dilute, it's not the buffer that's going to be producing most of the hydronium and hydroxide. It's going to be water, and if that's the case, the pH is going to go close to 7. Well, actually, this is supposed to be pH 7, so we're probably okay. But for other buffers, let's say you're making a pH 4 buffer, you don't want it to go to pH 7, and so we don't want it too dilute. The higher the capacity, the less impact one drop is going to have. And so if I add 1 drop to this versus 1 drop to this, I'll expect a more significant change. in the lower capacity buffer. So let's just try the two different capacity buffers. And so the first buffer I'm going to make is, I just need to make a solution that's going to be 0.63 molar of the base, which is HC2O4. Actually, what was my base? PO4, HPO4. Did I do that? Yeah, HPO4 2 minus. I got a pen failure, but I'm out of time anyway, so. I didn't finish chapter 7. I was planning to finish chapter 17. I need to talk about two more things. One is this buffer capacity stuff and buffering action. And two, indicators, which are buffers, buffer systems. So what I'm going to do is, we're not going to have the test for 17 next week. We'll have it the following week on Tuesday. I'll finish this up on Tuesday next week, okay? So exam 17, not next week. Tuesday of the following week. Is that okay? All right. Anyway, have a nice weekend. I'll see you guys Monday. Thanks. I don't know what lab. Do you guys know what lab we're doing on Monday?
Not off the top of my head.
Yeah, take a look. See when you